So welcome back, guys. I hope you had a good lunch, or perhaps on the East Coast dinner. We now move on to the lab part of this session. Today, we are going to look at one data set, which is I've deliberately crafted because it's hard for some algorithms. We will first analyze this data set using K-means clustering, and then we'll use DBSCAN. Now, the typical way one starts is that one gives some easy data sets, which you have nice globular data. And when you have globular data, then you can easily use K-means clustering to bring out its strength. I'm actually taking a different approach. I want to show that I will assume, and I'll give you some problems, homework problems in which you can validate that. Right? But I wanted to take a tough case to start with. So I created a data set. There is a data set in the cloud. You'll find it. It's called Smiley. And you will see shortly why it's called Smiley. Now, usually when you have the data, you don't know what. Oh, yeah. Data comes without labels. The whole point of unsupervised learning is you don't know labels. But here, I'm giving you the answer that it will tell you which cluster it belongs to. There are 7 clusters, which of the cluster each point belongs to. But remember, you don't cluster on T. That is sort of our secret. It's not something the algorithm should see. The algorithm should see just X and Y. So from this data set, you strip out X and Y, and you look at its description, and you then plot it out. And what do you notice? It looks like a smiling face. So I created this data. Now what we are going to do is, how many clusters do you see?
6.
6 clusters. And we also have outlier points, isn't it? All this poke marks on the face, pimples on the face. So we're going to see how well the algorithm is going to do. So what I do is we will run K-means for different values of K. Remember what I told you. You have to keep running K. If you don't know how many clusters really are there in the data, you have to keep running for different values of K. You have to make a scree plot and look for the elbow. If you remember the steps, because K is the hyperparameter of the model. So here it is. What I do is for K, and I just chose an upper bound of 16, right? Assuming that there are no more than 16 clusters possibly. And of course, you don't know. You have to be careful. You have to build the scree plots and iterate over it and see where the bend is. So K-means clustering is very easy. You just say, find these many clusters. How many clusters I find? Between 1 and 16. Find the clusters, fit, and then you can predict the labels, and then you can say, you can sort of append, the inertia is your WSS. Then you plot it out. So look at the first one. When K is equal to 1, is the clustering good? Of course it's good. The whole thing is one cluster, but it doesn't look like one cluster, isn't it? It looks like, well, 6 clusters have been merged into one cluster. Now, when K is equal to 2, do you notice how it has built the cluster sub, guys? Would you agree that it's good clustering? Not for the client. It almost feels as though, well, in the COVID days, it looks as though the person is wearing a yellow mask, isn't it? Well, it doesn't look like a good cluster. Half the top half and bottom half. What about K is equal to 3? Little bit better maybe, but nose has a bit of a yellow. It's a little bit better, but not really. The eyes and the eyebrow they should be separate clusters, hopefully. Well, that didn't quite work, but this looks reasonable, 3. What about K is equal to 4? K is the same as K is equal to 3, except that your lips have gotten parted, isn't it? Do you see the split in the lip? Right? So would you say this was a great job? Maybe not. What about K is equal to 5? Now what happened? Where are the 5 points? It is not visible. This is one cluster. This is second, third, fourth. Here, so here you have k is equal to 5, right?
In k equal to 4, why did it not do a split in the middle, and why?
It's just the way k-means ran. It's partly sensitive to initialization. In this case, not. It just so happens that it's looking for round clusters. For whatever reason, it decided that this is the best way to get a nice round yellow. You see that yellow is the problematic area, right? It ended up picking that as a cluster. And then it took a little bit of the nose and the other side of the lip as one cluster. Right? And you can quite clearly see the limitations of k-means.
Right.
Isn't it? You go to k is equal to 6, it's beginning to get iffy. Lip is wrong, but other things look right. Isn't it? It is, for example, not confusing the nose with the lip. Even k is equal to 5 is reasonable, at least everything looks reasonable. And thereafter, you start noticing something interesting. K is equal to 7. Now, for the first time, the eyebrow is separated from the eye on the left. Isn't it? Not much has changed. K is equal to 8. Interestingly, both the eyebrows are separated from the eyes, right? So everything would have been great except for this troublesome lip. The smile is getting the k-means cluster, is wiping the smile out of k-means clustering in some sense, right? Not quite good. Well, what about this? You would agree that from k is equal to 9 onwards, it gets progressively worse. Is splitting clusters, isn't it? Right? Until you reach k is equal to 15, and it is forced to find 15 clusters, and what it has done is found this. Right? So let us make the scree plot and see what it looks like. Right? Where is the scree plot? We get this. What we did is we saved the WSS, right? So let's plot it out for different values of. So here is the scree plot. You look at this. Now, where exactly is the elbow in your view? 3 or 5? Yeah, 3 or 5, right? So let us see how does the cluster 3 and cluster 5 look. Cluster 3 is this. One eye is one cluster with its eyebrows, second eye is another cluster, and then the nose and the lips, the smile are together, right? Maybe a reasonably good. If you think about it, and k is equal to 5 has split the lip, but other things it got right. Right? So k is equal to 3. These are, I mean, if you really look at it, arguably these are the better ones in this clustering, isn't it? Which one would you guys consider the best?
5.
5 is.
Yeah, except for the split lip, right?
Split lip
and outliers being dragged in. 3 is this. Okay, so this is it, guys. K-means clustering. Now, explain, why do you think K-means didn't work well on this?
because of the globular.
The shape of the data.
Yeah, the shape, it's not roundish. In this face, eyebrows and lips are not roundish, right? And that gets it into trouble. You notice that it always seems to get the eyes right. Right? You notice that never does it split the eye. It seems to get the eye right. So things that are roundish, it gets right, but things that are not roundish, it does not get right. It's a limitation of the K-means. But if you were to try it on globular data, it would work just well. Let me get back to that. Let's try the same thing with DBSCAN. Same data. This is the original data. I hope you recall that. Oh, what am I doing? Okay. You remember the face? And then this By the way, DBSCAN, the way the algorithm has been written, it's a little clumsy to come to know which are the real points and this. The API is a little bit clumsier to get the cluster labels out, but you'll get it. This code, they have given the example code on their scikit-learn website, and most of us pretty much write code almost or near identical to that for the purposes. So this is it. You get the labels, and then you look at each of you do the same thing. You say, all right, now that I found clusters, let me tell. So you ask this DBSCAN, how many clusters are there? You know, this is not a question you could have asked K-Means, but DBSCAN you can ask for clusters. What does it say? There are 6 clusters. It says there are 6. Does that look correct? Looking at this picture, would you say there are 6 clusters? There are 6 clusters. So it seems to be getting right. And let's see what it marked as clusters. Now, see, this is how it calls the clusters. All the gray points are the outliers, and all the clusters are colored. Would you agree that it seems to have gotten it right? So that is the advantage of density-based clustering, that it works for non-globular shapes also. Right? And it's a lesson here. Now, today, I kept the lab to something actually very, very simple for clustering. Clustering is simple. It is as simple as that, K-means and that. Now, one lab is missing, which is the hierarchical clustering. I'll also put on hierarchical clustering. And I have only put on the tough ones. Actually, I could put on some easy clustering labs also. Like, for example, if you take data, let's say that you hand create data that looks like this. Let's look at this data. Do you think clustering will work? K-means will work?
Yes.
Yeah, and why will it work? Because globular nature, right? It will get it this. It will make it correct. So I'm going to post this data as homework for you. Try to do K-means clustering, etc. See that it works, right? Obviously, will DBSCAN work on it? Surely it will work. And well, of course, this is the Smiley dataset. So this is it. Clustering is very simple. When you do the labs with it, you'll realize that it's a very simple algorithm. Hierarchical clustering, actually, I wanted to bring the lab, but I didn't. I don't know what I did with the lab, but it had a few linkage functions, you know, the different kinds of distances between them. And to show you the difference that it makes, I'll post that lab, and maybe next time we'll walk through it, or Tuesday we'll walk through it or something. Or you can read it on your own. I believe that this is very simple code, right? All of these algorithms, like say, for example, K-means algorithm, you would agree that this code is one-liner to create, like, look at the inner loop. If you set your value of K, a cluster, is the same fit and predict that we are used to, isn't it? Now, this something is odd about it. It is unsupervised learning. So why is it using the word predict? It's an abusive term. What it is, it should be more like assign each point in the data, assign it to a label, to a cluster. That's how it is. But since people are used from regression and classification to fit and predict, I suppose that's why the creators of the scikit-learn library chose to keep the word predict. But remember, clustering is not a prediction algorithm. Right? So that is that to the lab, guys. I wanted to keep the lab simple. Go ahead, Ani.
So for DBSCAN, how do you choose the hyperparameters? Do we always have to visualize and check?
Yeah, I'll show you. Where is the DBSCAN part gone? Yeah, epsilon and minimum number of samples. So actually, I deliberately was hoping nobody would ask that question, because that's exactly your homework. The homework is play around with different values of epsilon and number of points, and see here in this line of code, where is the DBSCAN gone? DBSCAN, do you notice this line? You have to choose epsilon and minimum number of points, n points in the, you know, this too. So these are the two hyperparameters in the model. How do you choose them? That's a problem. Now remember, we mentioned that's a problem. You have to guess. You have to guess and choose and see which of them gives you the best clustering. So for example, if you make epsilon is equal to 10, see what it does to your clustering, right?
Do we every time have to visualize and see if there's no metric to check?
Yeah, I mean, there is a metric you can, for each of the clusterings, you can observe the WSS and things like that. The same thing that we did for K-means, right? Remember, we use K-means. Né? You could build the same plot and see at what value you get good WSS of epsilon and a number of points, right? So see, and this is one of the part of machine learning. People often ask, why do I have to keep on doing experiments to find this best? You can automate it, building a loop and so on and so forth. So there is this emerging field, and we'll have one of the sessions called automated machine learning. Guess what it does? It not only finds the best parameters, it finds the best hyperparameters, right? So if you use automated machine learning, which is all the rage, I mean, all these cloud providers are very big on, oh, we'll give you automated this and that. So the idea is that it will keep on trying different values of the hyperparameter and see which is the best and tell you that as the answer. Oh, yes, lots of computation. So if you're in the world of machine learning, the first thing you need is you need good hardware. So one of the experiences for people in this class is if you are sitting on old laptop, 3, 4, 5-year-old laptop, the first thing people end up doing after some time is doing what? Upgrading the laptops because things don't run on the older laptops. It's a lot of computation in general, but see, today's hardware has become very powerful. Like if you ask for the Smiley dataset, it is too small and the math is too powerful. It will run just fine on any laptop. And you could try out hundreds of combinations of epsilon and number of points, and it will barely take a minute, right? So, but when the dataset sizes are huge, then it becomes a concern, right? And so that brings up one of the interesting problems. Why do I have to randomly try all these possibilities? Is there a way, just like we do gradient descent in parameter to find the best parameters in linear regression or classification? Remember, we did a gradient descent on the loss function. So can we not apply a method like that for the hyperparameters and quickly go from one bad set of hyperparameters, quickly find the shortest path to a good hyperparameters of the model instead of randomly trying many things? And that is the whole field. That's a core area of automated machine learning. It is called Bayesian inference or Bayesian optimization. You will learn about it in the next workshop, right? Because it's a bit math heavy topic. So we'll learn about it in the next workshop. Because we'll have to know things like a KL divergence and things like that. So we'll do it along with the engineering math. So any other questions, guys? Anybody? So this looks easy, isn't it? Clustering is easy, guys. It's very easy, right? The theory is easy, and at least the standard, some of the simpler algorithms, theory is straightforward, and so is the practice, the doing of it. Right? Yeah, go ahead. Oh yes, I have to post it on the course page. I'll do that. Just like all of you, I have also been busy having fun with Diwali now. Time to get serious.